Boom! Yes, folks, Hume here again. How are you going? So this is the 5th video in our series on factorization. Brief recap up to this point. Factorization 1, univariate binomial. Factorization 2, the bivariate binomial. Factorization 3, factorization by grouping or factorization by groups. Factorization 4, where we got into the quadratic expression. Factorization, now we call it 4b, which was one video that was a continuation of factorization 4, where we specifically consider the cases of the quadratic where b was equal to 0, c was equal to 0, or where both b and c were equal to 0 at the same time. And now we run straight into this video, which is factorization 5, where we're going to deal specifically with the case of the difference of two squares, which we encountered coming down to the end of factorization 4b, right? The second video on the factorization of quadratics. And at that point, we saw that x squared minus 25 was equal to x minus 5 into x plus 5. And we agreed, based on the commutative property, that that is the same thing as x plus 5 into x minus 5. So it really doesn't matter which one you put first. That is simply a matter of personal preference. Yeah? This particular relationship, this particular instance, this particular case is a special case of a general relationship, which we call the difference of two squares. And what relationship is that? All right, so that relationship is where we say that a squared minus b squared is equal to a minus b into a plus b, or for those of us who prefer to do it the other way around, is the same thing as a plus b into a minus b. Either way you want to write it, absolutely no problem. So this is a general relationship. And just as we did here in the last video, I will expand out these two just to drive home the point that a squared minus b squared is equal to a minus b into a plus b, or a plus b into a minus b. I just want to make sure that nobody spends time fiddling with this and wondering whether a plus b multiplied by a minus b is the same thing as a minus b multiplied by a plus b. Right? So we're going to expand it now. Let me just rub off here. Alright? And we're going to say that we're expanding it. So we're going backwards. Flip side, back side of the same coin. Right? So if we have a minus b into a plus b, that is equal to a by a is a squared plus ab minus b by a is minus ab, or minus ba, same thing. Minus b by plus b is minus b squared. Minus ab, sorry, plus ab minus ab is equal to a squared minus b squared. Or we could have a plus b into a minus b. Same thing, just switch the order. A by a is a squared. A by minus b is minus ab. Plus b by a is plus ab. And plus b by minus b is minus b squared. Minus ab plus ab is 0. So you get the same a squared minus b squared. Yeah? So whether I have a minus b into a plus b or a plus b into a minus b, is the same a squared minus b squared. So I'll take the extra time to expand it to make sure that you see for yourself that a squared minus b squared is equal to a minus b multiplied by a plus b. Or vice versa, a plus b multiplied by a minus b. So based on the knowledge of that relationship, we have the opportunity now to do a direct factorization of any expression that conforms to the format of a difference of two squares. So once we can recognize, very important word, once we recognize an expression as the difference of two squares, then the factorization is quick, easy, simple, and efficient. Right? I have been saying for years to anybody who would listen that factorization of the difference of two squares is the easiest factorization you will ever do in your life. You will never get a factorization easier than that. That is the one question in the factorization that you could definitely do in one line, and it is based solely on recognition. Recognition of the perfect square in an expression where you have a difference between two perfect squares, which goes back now to knowing your squares and your square roots, right? I always tell my students, you must know your squares and your square roots in the same way that you must know your tables, your regular multiplication and division tables, right? Your squares and your square roots is part of that, because your squares is same multiplication, you know. It's just something multiplied by itself. So instead of multiplying 4 by 3 or 4 by 5, you multiply 4 by 4. And that is 4 squared, which is equal to 16. And 8 squared is equal to 64. And 12 squared is equal to 144. Most students would know from 1 to 12, right? And in the context of Trinidad and Tobago, the reason for that is simply because on the back of the copybooks that we get in school, you have all the multiplication tables from 1 to 12. So you find that when people have to deal with 13 squared and 15 squared and 18 squared, we have a problem. And I always encourage my students, my mathematics students in school, and even the adults, you must know your squares and your square roots from 1 to 20. Alright? You must know your squares and squares from 1 to 20. It makes your life a lot easier if you could recognize 15 as the square root of 225. Or if you could recognize 289 as the square of 17, etc., etc., etc. And for my students who do in add maths, I generally encourage them to go a little further and memorize the squares and the square roots from 1 to 30. Right? Now, the squares and the squares between 20 and 30, they don't usually come up in an exam setting, but if you have them at the tip of your fingers, it makes life a lot easier. Right? But at the very minimum, for all math students, your squares and your square roots from 1 to 20, absolutely essential. Don't even try to run away from it. Right? Nice. So once you can recognize a perfect square, then you don't have a problem. A perfect square is simply a number that has an exact square root. Or, not just a number, but an expression that has a perfect square root. And you will see examples of that we're going to do now. So, if you have, we're above the board now, right? Let me clear the space. So if you have, let us say, x squared minus 256. See the numbers I'm using? No. Let me start with the x squared minus 25. So in other words, let us say you're in an exam and they tell you factorize x squared minus 25. You don't have to do anything fancy there, you know. all you could do is just say x squared minus 25 is x minus 5 into x plus 5, or vice versa. If they tell you factorize 25 minus x squared, flip the order, then the answer is 5 minus x into 5 plus x. And that's it, you know. That's it. Now, sometimes in terms of writing it, what some students do is this. So for this, they would say x squared minus 25 is equal to x squared minus 5 squared, right? And then you say one more line, x minus 5 into x plus 5, not a problem. And over here, they would say 25 minus x squared is equal to 5 squared minus x squared, which is equal to 5 minus x into 5 plus x. Right, so this line is not absolutely necessary, but if you need this line just to make things a little clearer for yourself, by all means, go right ahead. So the bottom line is, if you could see an expression where you clearly have a difference, and then you could express that as a difference of two squares, in this case x squared minus 5 squared, in this case 5 squared minus x squared, then the next line is to just write out the factorization based on the knowledge of the difference of two squares. So you don't have to go through any long set of working with a and c and all them kind of things. Just difference of two squares. End of discussion. The easiest factorization you'll ever do in your life is the difference of two squares. Alright, so let me do a few more examples just to drive the point home. So for example, let us say you have p squared minus 256, right? If you go in an exam and you see factorize p squared minus 256, the only problem you would have here is recognizing 256 as the square of 16. And that is why I say you must know your squares and your square roots from 1 to 20. Because for general exam purposes, they don't usually go outside of that. You will hardly find, for example, a question where they would say factorize, let me see, 23 squared I think is 529. I don't have everything down with it 20 to 30 here, but yes, 529, right? So you hardly find in a maths exam, they'll tell you factorize 529 minus w squared. You'll hardly find them going beyond 20, right? So as an absolute base for yourself, make sure you know the squares and squares from 1 to 20. So if you see this, you know immediately that your answer is p minus 16 into p plus 16, right? So in other words, don't just be satisfied with squares and squares from 1 to 10, right? Or from 1 to 12. You need to go a little beyond that. Stretch yourself to 20, right? Nice. Next example. Again, and we could flip the order, right? So now just to finish this one here out, right? Finish out this one. 529 minus w squared will be 23 minus w into 23 plus w, right? But of course, it depends on recognizing 529 as 23 squared. At least learn up to 20 now, right? So that if you go in an exam and you see this, you see a square here, and you see a minus sign here. So something in there might tell you, well, all right, maybe it's a difference of two squares. And then you check your 529, you run through it on the calculator, and you realize, well, 529 is 23 squared. And you proceed, right? Bottom line, 1 to 20, squares and square roots. right? So we do some more examples. Now, of course, the perfect squares don't always have to look as simple as this. You could have the perfect squares could be a little more complicated too. Eh? Watch some other forms that the perfect squares could take. So in other words, remember we just said that the perfect square is a number or an expression. Let us use the word entity to cover all cases, right? A perfect square is an entity that has integer square root. No, if we use in letters, we can't say integer. A rational square root. We could use rational too. All right. The vocabulary kind of slipping here now in terms of covering all cases. But the point I'm making is that you could use letters as perfect squares too. And watch what I'm going to do now. So if you have an expression like, let me say, k squared minus 441m squared. You see? Of course, you're seeing that k squared is a perfect square because it's k squared. If it's k squared, it has to be a perfect square, right? The 441m squared. So you see the m squared here. Then 9 times out of 10, you could tell yourself, well, yeah, maybe it have a perfect square in there somewhere. But again, you have to recognize that 441 is the square of 21. So you can write this over as k squared minus, watch it now, 21m in brackets squared. See? So you have to be sure-footed where your indices are concerned. And here is where the difference of squares could get a little complicated. Because the set we just did there is pretty straightforward, right? X squared minus 25, no problem. You could see that. You're familiar with that. 25 squared root of 25 is 5. K squared minus 256, or P squared minus 256, or 256 minus P squared. You ain't really sure, but you could run the numbers quickly. Let me see if 256 is a perfect square, no problem. So you have the P squared, and you have the 256 in the same line. You could kind of guess that is, yeah, perfect square. 441 is a hint if you're familiar with it. If you watch this expression and I'm not sure, you can check it. But the 441m squared here, that is the catch. Because now we need to know the exact expression that will be the square root of 441m squared. So even if you recognize that 41 is 21 squared, how do you go about writing it? Right? So remember, now I'm just taking a little sidetrack here. You have to remember that 21m squared is the same thing as 21m multiplied by 21m, which is 21 squared. Well, remember multiplication is commutative, so basically what you have is 21 by 21 multiplied by m, which is the same thing as 21 squared multiplied by m squared. Right? So all of this is part of this, right? It's kind of almost taken for granted, but as we go a little deeper into it, you will see that this is important. So you need to be aware of this. This is the indices that we cover in a separate video, but we're coming back across here now. So k squared minus 21m all to be squared. Or some people might write it as k squared minus 21 squared m squared. Either way, same difference, right? And then after you do that, your very next line would be, having recognized that 21m all to be squared is the same thing as 21 squared by m squared, which is 441m squared. Then your next line would just be k minus 21m into k plus 21m. Of course, you'll be able to move from there to there with sufficient practice, right? But the key, whether you recognize it or not, is recognizing this as a perfect square. And having recognized it as a perfect square, knowing exactly what the square root is, which is 21m. Right? So we're going again. Next example. Let us say you have something like, I have an example here. 49 a squared minus 324b squared. Aha! Things start to get nice now. So even what I insist on referring to as the easiest factorization you'll ever do in your life, even that factorization has some challenging moments that if you're not careful, you could find yourself running aground. Which is why even with the easy topics, you have to practice. Don't make the mistake of thinking, well, yeah, he explained it, and he explained it real good, and I understand it, and I know it, and then you just ignore it. You have to practice, right? I don't know anybody who will look at a YouTube video of somebody flying an aeroplane and think that they could fly an aeroplane without practice. I mean, the thought might cross your mind, but you'll have to be an absolute madman to try that in a serious way without proper practice. Right? Maybe if you're in an emergency and there's no other alternative, you might try a thing. But you will know that you're trying a thing. You wouldn't sit down with any idea or any notion that you know what to do just because you understand the explanation that somebody give. So don't confuse understanding an explanation with understanding how to do what the explanation explaining, if I could say that, right? You could understand the explanation, you could follow the points, you could follow it in your head. But there's the aspect of muscle memory of knowing what to do. That is a whole thing by itself. Don't underestimate that. It's the same principle when you learn maths. You see the difference of two squares, they say, yeah, that easy man, braps. You had to practice it still. Right? So back to this guy here. 49a squared minus 324b squared. Again, recognition. So you know your squares and your square roots from 1 to 10. You know that 49 is 7 squared. So you can write this over immediately. So you see what we were talking about a while ago with the 21 squared m squared, right? So you could write this over as 7 squared a squared. See? Minus 324. What's the story with that? Again, you either know it as 18 squared, or you double check that, you watch the question and you see, I see a square here, I see a square here, I see a minus here. There's a difference. I see a 49 here. I see, Right, I know 49 is 7 squared. So maybe it's a difference of 2 squares. Common sense, simple thing, right? Well, the common sense part is simple, right? In the sense of you have enough clues here that will tell you that maybe the question is a difference of 2 squares. So even if you don't know the square root of 324 by heart, you have enough things that will tell you, well, alright, maybe let me double check this. And if you have a calculator, double check it and you realize that that is 18 squared, b squared. So you see the format, same thing we just had a while ago. Look at here, right? So 7 squared by a squared, the square root of that will clearly be 7a. And the square root of this will clearly be 18b. So when you're factorizing the difference of 2 squares, that's this square here, that's this square here. Perfect square, then you have 7a minus 18b in brackets here, and the 7a plus 18b. Or 7a plus 18b multiplied by 7a minus 18b. Right? So this is the kind of thing that you have to be able to do. So as I was saying, in a slightly different circumstance a while ago. It is rare that in an exam you'll get something like, let us say, 289 k squared minus, I think 676 is a perfect square too, you know. 26 squared is 676, beautiful, right? 289 squared minus 676 p squared, right? Most examiners generally, now maybe if it's a more difficult exam, you might get it. Maybe in an advanced exam, you might get that as part of some other question, right? Or maybe if it's a slightly more difficult maths exam, and we have a lot of those in different parts of the world, right? You might get 289 k squared minus 676 p squared, which is to say that you have to recognize 289 as the square of 17, and you have to recognize 676 as the square of 26, right? They generally wouldn't do that. They will probably give you something like, let me say, 64 w squared minus 29 squared is what? Let me see, boy. 29 squared. I ain't sure what that one. 29 squared is 841. 64 squared minus w squared minus 841 v squared, right? So in other words, they include numbers in the sum that they know you'll be familiar with. 64. They know that most people know that 8 squared is 64. So that in and of itself is a clue. Even if you didn't recognize 841 as the square of 29, the 64 here, which is the square of 8, perfect square. You have w squared here, you have v squared here, and you have a minus sign here. So, I mean, tell yourself, well, maybe it's a difference of two squares, right? And once you start to go down that line, you start to write now. Well, all right, 64 is 8 squared w squared. You ain't really sure what 841. So here now you might have to go and spend a couple of minutes with the calculator, fiddling and diddling. No problem. But after you fiddle and you diddle, you realize, well, all right, that is the same thing as 29 squared by v squared. And then you factorize now 8w minus 29v into 8w plus 29v. Right? And same story up here. We would have had 17 squared k squared minus 26 squared p squared, just to make sure to your own self. So your final answer now would be 17k minus 26p into 17k plus 26p. Right? End of discussion. Beautiful. Right, so let us go on now to another level of the difference of two squares. And in this level, the difference of two squares, the perfect square, is not obvious from the first line. Every example we have done up to this point, as soon as they watch the first line, they realize, aha, perfect square. So, how about this example now? Let us say we had to factorize 27 m squared minus 48 n squared. You could get one of them too, right? So you see the two squares, no problem. You see a subtraction sign, so you tell yourself, aha, this might be a difference of two squares, right? Except that 27 is not a perfect square. 48 is not a perfect square. So you tell yourself, how are we going to factorize this? Because you're already looking at it and you're suspecting that it's a difference of two squares. So what do you do in a case like that? Do you go trying to force these squares here? Or do you then go and do something else? Well, we have options. Because if we treat this as a bivariate binomial, right? Binomial, two terms in the expression, bivariate because they have an m and an n, two variables. No problem. We cover that in the second video in factorization. Then we could take out 3 as a common factor because 3 into 27 is 9, 3 into 48 is 16. So again, 16 by 3 is 48. You had to get familiar with the multiplication tables beyond 12. So you need to know, for example, that 15 by 5 is 75, or 16 by 3 is 48, or 18 by 3 is 54. 19 by 4 is 76. 17 by 3 is 51. 14 by 4, 56. 13 by 5 is 65. You need to be aware of these kinds of numbers. Don't just stop up to 12. Mathematics doesn't stop at 12. Multiplication doesn't stop at 12. You go in the maths exam and you see stuff like this. What are you going to do? Right? So you have to get familiar with numbers beyond 12. Right? So you factorize now. You see 3 into 9m squared minus 16n squared. And boom! All of a sudden, now we have a difference of 2 squares inside the bracket. See? So you have a common factor outside, and inside the brackets you have a difference of 2 squares. And of course this would be then 3 into 3 squared m squared minus 4 squared n squared, which would then be 3 now into 3m minus 4n into 3m plus 4n. So sometimes when you're factorizing, you will need to take out the common factor first before the difference of 2 squares becomes visible. Right? In the examples we have done so far, the difference of 2 squares, you could see it from the first line. And even if you didn't recognize one of these squares, you had enough to go on to do a little investigation and realize, hey, we have a square here, a perfect square. But we have a situation here now where you see the difference, you see these squares, you see the 2 squares, but then you realize we don't have a perfect square here. However, when you take out the common factor, boom, all of a sudden, you now have a perfect square inside the bracket. So you have to be able to do stuff like this as well. Right? We could go a little further now, where along the same lines of a common factor, this time, instead of the common factor being a number, in this case the common factor was 3, you can also have the common factor being a letter, a variable. Let me do one like that. Right? So if you have one, let me say you have, find an example here. Let me say you have 20n cubed. 20n cubed minus 125 n m squared. Woo! Yeah, man. Now, the thing with this example is that you have more than one common factor. So you have a common factor as a letter and a common factor as a number. Because watch, you have cube and you have nm squared. So in other words, looking at this, there is absolutely nothing here that would suggest a difference of 2 squares. In all the examples up to this point, there was a clear something squared minus something squared. And in the last example, even though we didn't have perfect squares in the first line, the mere fact that you saw these 2 as the power, the square, that alone would set off an alarm bell in your head to suggest to you that, okay, maybe it's a difference of 2 squares here. We have 2 squares and we have a difference. So maybe we have a difference of 2 squares, right? Here we have a difference. The only square we have here is nm squared. Here we have n cubed. So we absolutely sure that we're not even thinking of doing difference of two squares in the first line. Maybe it might come up later on, but at the very first step, you have to do something else, your regular factorization. So always be prepared to factorize regularly first before the difference of two squares becomes apparent. Right? Not every question on the difference of two squares is one where as soon as you see it, you know immediately that it is in fact a difference of two squares. Sometimes you have to pull out factors first, and then you will see the difference of two squares inside the bracket. So for example, in this case, you have 20n cubed minus 125nm squared. So let's deal with the numbers first. Right? So you take it out and you have 5 into 4n cubed minus 25 nm squared. Right? So you see 4 here and you see 25 here and you see, 4 is a perfect square and 25 is a perfect square. But we ain't finished the factorization in here yet. Right? Because we have an n cubed here and we have an n here. So we have n as a common factor as well. So you have 5n now. You take out the 5 by the n. 5n into 4n squared minus 25 m squared. And boom! It took you 2 lines to get here. But no, we have a difference of two squares. Right? But you also have a 5n outside, which you have to maintain. You have to retain, sorry, all the way through until the end. Right? So you have 5n here into, let me say, 2 squared by n squared minus 5 squared by m squared. Right? As I get more proficient, this line will not be necessary, but I am including it here for the sake of instruction. Right? And then you would have, yes? Okay, I just checking something on the camera there. So now we factorize, you get 5n into 2n minus 5m multiplied by 2n plus 5m. And that is your factorization of the difference of two squares. So sometimes you can have a number as a common factor. Sometimes you can have a letter as a common factor. Sometimes you can have a number and a letter as a common factor, as we had here. So let me just do one with a letter alone, just for the sake of completeness, and that will be the end of this particular discussion on the difference of two squares. Right? So let me see. I don't think I have any examples written on here. So let me pull one out of the hat. Well, let's see it. Let me come up with something. Let me refer to my page here first. Hey, Papa. Alright, so let us say, for example, yeah, let me use a common example that I like to use. This is an example that I've been using for a long time. And I think, if I'm not mistaken, this was actually a question on our CXC maths paper some years ago. So in a CXC maths paper some years ago, they tell them to factorize p cubed minus p. No problem, you know. You have nothing there that suggests difference of two squares. However, you have a univariate binomial. The variable is p. So you say, well, alright, that is equal to p into p squared minus 1. See? You take out the p, you have p squared minus 1 inside the bracket. And then you go from p into p squared minus 1 to p into p minus 1 into p plus 1. Simple dimple, you know. Simple dimple. Right? So, in factorizing the difference of two squares, you have various levels of the question. In one level, you will have a question. As soon as you see it, you know immediately that it is a difference of two squares. And the perfect squares are simple enough that you can recognize it immediately. Usually squares of numbers between 1 and 10, right? Most people are familiar with those. And then you'll have the same type of question where the squares are a little beyond 10. 15 and 18 and 17 and them kind of numbers, 14 and things, right? Those are the numbers that folks are not as familiar with. Familiarize yourself with them. And then the other level would be where you have perfect squares where it's not just a simple number or a simple letter, but you have letters and numbers coming together. So the example we did was, we had an example, 49a squared minus 324b squared. So your indices come into play now. So you're recognizing the numbers, but you also have to combine the numbers and the letters when you're dealing with your squares and square roots. So you know, for example, that the square root of 49a squared is 7a, because you could write 49a squared as 7 squared a squared. Same thing for 324b squared. The square root of 324b squared is 18b, because 324b squared could be written as 18 squared b squared. And then we had the next level where you had to do a preliminary factorizing first. So in those questions, they might tell you factorize completely, right? This is an example of that. Factorize completely, because you could factorize here. And if you're not aware of the difference of two squares, you will stop here and tell yourself you're finished. But no, you had to factorize now p squared minus 1 into p minus 1 into p plus 1. Right? Your common factor could be a letter, as we have here, a variable, or a number, as we had in the example before, 27w squared minus 48v squared. Right? And in the question that we did, at the end of the last video, we had a situation like that, where we had, I think it was 2x squared minus 50, right? And when you factorize, you got 2 into x squared minus 25, which, when we factorize, you got 2 into x minus 5 into x plus 5. So in this case, you had a number as a common factor, which when you pull it out, you're left with a difference of two squares inside the bracket, right? And then we had a slightly more difficult example with the 27w squared minus 48v squared. And the last example we had before these two here would have been the 20n cubed minus 125mm squared, where you had both a letter and a number as common factors to be taken out, which would then leave you with the difference of two squares inside the brackets, which is just pretty straightforward factorization. All right, so I trust that these examples in this particular video and all the examples in the preceding videos would have shed some light on the topic of factorization for you. And I want to make a special appeal now for you to practice. If you had followed all the videos, then you would realize at some point that I have my own questions attached to the videos. Get them and practice. If you want to get questions from another source, not a problem. Just get questions and practice, because you're not going to get that fluency without the practice, right? As in everything else, some folks will catch it a little faster than others. But if you are one of those who taking a little longer to catch it, it just means you have to spend a little more time with it, that's all. That is all. And once you're willing to put in that extra time, eventually you'll get to that level of proficiency where you could express yourself correctly with the same or a very similar level of proficiency as the person who catch it fast. And the whole idea is to maximize yourself, to do the best that you could possibly do. You don't have to worry about anybody else, just do your best. And then go beyond your best. You do that and you're good to go. Alright? So, as always, go forth, do what you have to do in the maths, do what you have to do in other areas of your life. Stay tuned. We have more things coming.